This is the trig application section. This is Unit 5, Day 2. And you see here are the objectives, so make sure you check back and make sure that you've accomplished these. And let's begin with lecture. This section deals with application of trigonometric ratios that we talked about yesterday. And so there are two things I want you to know. The angle of elevation is the angle formed by a horizontal line and the line of sight. So if I am standing on this balcony and I'm looking off in the distance horizontally, that's the horizontal line, and if I have to look up to see the airplane, that angle is called the angle of elevation. If I look down from this balcony to see a car on the street, that angle is called the angle of depression. So both of these are referenced from a horizontal line of sight, either above the horizontal line of sight or below the horizontal line of sight. So we will solve problems using the angle of elevation and the angle of depression, and basically all these are our application problems of trig ratios. It's exactly what we've done before. So the first one, find the approximate height of this tower. Well, I have a person standing here at a distance of 125 feet from the base of the tower, and they look up to the top of the tower, and that makes a 57.2 angle of elevation. So what you need to be thinking about is that we have a right triangle. We know one side is 125 feet. We know this side is 57.2 degrees, and I would like to know how tall the tower is. So given my angle of 57.2 degrees, I have been given the side that is adjacent to that angle and the side that is opposite of that angle. So that would be the tangent function. The tangent of my angle equals the opposite side, side A, over the adjacent side, which is 125 feet. So solving for A in this case becomes a multiplication problem because the two are right next to each other. The tangent of 57 degrees times 125 feet gives us the value of A, which is 193.96 feet. Often I will ask you to round to the 10th place, 194 feet. Let's look at the next one. Find all missing parts of a right triangle. A building is 21 meters tall. That's given for you right here. It casts a shadow 25 meters long, also given for you. Find the angle of elevation, so that is marked here, the angle of elevation of the sun, and find the angle that the sun shines with the building and the hypotenuse of the triangle formed. So one of the first things I want you to realize is that we have the angle of elevation for our right triangle, and that angle of elevation is right here. And we know that this building is 21 meters tall, and we know the shadow is 25 meters long. So we are aware from that angle of the opposite and the adjacent sides, so that would be the tangent function. The tangent of that angle of elevation equals the opposite side divided by the adjacent side. So the tangent of that angle is 0.8. So I would like to know what angle has a value whose tangent is 0.8, and that is a 38.66 degree angle. The inverse tangent of 0.8 is 38.66 degrees. So that is our angle of elevation. And interestingly enough, that is also the angle that the sun makes with the building. Those two are the same. The angle that the sun shines with the building. And so now we need to find the hypotenuse of the triangle formed. And I think the easiest way to find side C is to use Pythagorean theorem. A squared plus b squared equals c squared. So 21 squared plus 25 squared is equal to c squared. So we will actually end up taking the square root of both sides and finding out that c is equal to 32.65. meters, the hypotenuse of the triangle. Okay, next problem. At a certain time of day, the angle of elevation of the sun is 40 degrees. To the nearest foot, find the height of a tree whose shadow is 35 feet long. And so here's what I want to show you. So here's my tree, and up here is the sun, and that sun makes an angle of 40 degrees, and the tree casts a shadow that is 35 feet long. So that's how your diagram would work. The hardest part is deciding how to draw these. So I have an angle of elevation of 40. I have a tree that forms my perpendicular, or the right angle to the ground. Again, that's my line of sight. I have to look up 40 degrees to see the sun in the sky. Excuse me. And the shadow of the tree is 35 feet. So now, to the nearest foot, find the height of the tree. That's what I would like to know. So with my given angle of 40 degrees, I have the opposite side and I have the adjacent side, again referencing this 40-degree angle. So tangent of 40 degrees is equal to the opposite side, which is the height of the tree, divided by the adjacent side, which is 35 feet. So tangent of 40 times 35 feet will give me the height of the tree, which is 29.37 feet. Okay, let's look at another one. The Washington Monument is 555 feet high. If you stand 1,320 feet from the base of the monument and look at the top, that would be the angle of elevation, and I would like to know what that is to the nearest degree. So the first thing you need to do is make a sketch. Go ahead and do that. Okay, the angle of elevation is what I want to find. So, angle of elevation, that makes a right angle with a horizontal. Now this Washington Monument is 555 feet tall. I am standing 1,320 feet from the base, and again, this is opposite over adjacent. This is a tangent application. 555 feet divided by 1320 feet, and so the tangent of my angle is 0.42045. Again, always carry that out at least 4 places when you're plugging this into your calculator. So the inverse tangent of this decimal number will give me the angle measurement, which is 22.8 degrees. There we go. Okay, there's one other thing that I want to discuss that is actually to prepare you for tomorrow when you work on your virtual vector lab. And so keep this thought for tomorrow. But I'm going to make this point here that is 4 meters on the x direction and 3 meters high. And so when I make that point, I could talk about how far I am away from the origin as the crow flies, which I am 5 meters away. Or I could talk about how far I am in terms of x and y coordinates. And in terms of x and y coordinates, well, I went 4 meters to the right and 3 meters up. So there are 2 ways to describe this point. I can use x and y coordinates, 4 meters positive for x, 3 meters positive for y, or I could express this in terms of what's called rectangular coordinates. This one right here is rectangular coordinates. Rectangular coordinates have x and y coordinates. Or I could express this in terms of what's called polar coordinates. And so the polar coordinates are expressed in the form r, which is the resultant or the hypotenuse. So r is the hypotenuse. And then theta is the angle from the origin, basically from the x-axis. So I'm looking at this angle. And this particular one I'm actually going to need to calculate it because I didn't do it before. So if I would like to use the sine function, the sine of this angle is equal to the opposite side over the hypotenuse, or the sine of this angle is equal to 0.6. So if I want to find what angle is associated with a ratio of 0.6, that would be the inverse function. So the inverse of 0.6 yields a 36.87 degree angle. So the way I could express this in polar form is that I have the hypotenuse is 5 meters long. That would be the hypotenuse, r, and that's sometimes given in these bar on either side, and that's meant to signify the absolute value of the distance or the displacement. It's actually 5 meters from the origin, and then it is at a distance rotated counterclockwise of 36.87 degrees. Because in lab tomorrow you're going to spend some time setting up situations of these rectangular coordinate systems and finding the polar form expression, or given the polar form, find the rectangular form, and then also convert from one to another, but also add vectors in the polar realm and determine the rectangular coordinates. So I just wanted you to make sure you knew what rectangular coordinates and polar coordinates are for tomorrow. Have a great day.